So to finish up our discussion of thermodynamics, what we're going to do is we're going to talk about the first and second laws of thermodynamics. Now the first law we sort of danced around, we talked about it a little bit with our calorimetry problems, but to set this up, basically let's go back to basically the way that we've been keeping track of energy for mechanical systems, because what the first law is going to do is tell us how to keep track of energy for thermodynamic systems. So for mechanical systems, we said that basically what we're going to do is we're going to keep track of the initial kinetic and potential energy, the final kinetic and potential energy, and then the work done by all the non-conservative forces in the system. And so I can rearrange this equation and get the change in the mechanical energy of the system, the change in the energy of the system is equal to the work done by non-conservative forces. So what this tells me is that keeping track of how the energy changes in a mechanical system is all about keeping track of the work done on the system by non-conservative forces. So we know our conservative forces will transfer the energy from kinetic to potential, back and forth between kinetic and potential. But in terms of changing the overall energy of the system, you need non-conservative forces to do work in order for that to happen. So when there isn't any work done by non-conservative forces, then the energy of the mechanical system doesn't change, which is, of course, another way of saying energy is conserved. Thermodynamically, what the first law of thermodynamics tells us is how to keep track of the energy for a thermodynamic system. It says that you can change the energy thermodynamically, so the internal energy of your system, you can change that energy thermodynamically by either transferring energy in or out as heat, or by the system doing work. So in this case, the system doing work would cause it to lose energy, which is why that minus sign is there. So keeping track of how the energy changes in a thermodynamic system then is all about keeping track of the two ways that we can transfer energy into or out of the system. We can do it as heat because we have things at different temperatures, or we can let the system do work or do work on the system. And so delta E is just keeping track of how energy gets transferred into or out. Again, Q, just like what we've done with our specific and latent heat problems, Q is our answer is going to be the energy transferred into or out of the system as heat. And if you're transferring energy into the system, so if your system takes that energy in, then Q will be positive. If your system gives that energy up, so it's transferring energy out of the system, then Q would be negative. So what's the first law tell us about an isolated system? Well, an isolated system, by definition, right, this is something that we take and put inside our insulator, and it can't exchange energy or matter with the surroundings. The only thing it can do is rearrange the energy inside. So the energy of an isolated system has to be constant, which means that the change in the internal energy of an isolated system has to be zero. And this is basically what our calorimetry problem is. Right? We're saying that we're not adding or losing energy to the surroundings. All we're doing is exchanging energy between the parts that are already inside our calorimeter. So let's add the second law. And so the first law tells us about energy. The second law tells us about entropy. And again, entropy is going to be one of these things that we just don't have a great definition for. But we'll talk a little bit in class about kind of what is the best definition that we do have for it. So what the second law of thermodynamics tells us is that the entropy of an isolated system cannot decrease. So in the same way that we just wrote for an isolated system, delta E equals zero, right? The change in the energy is equal to zero. The change in the entropy for an isolated system is zero if the process is reversible, you can undo it, or it's positive if the process is irreversible. And the way the world works is basically any real world process is irreversible. And our sense of time, our sense of how things flow within the universe all that is really based on sort of our understanding of knowing what entropy is allowed to do. So a reversible process is a process that can be reversed so that it leaves no change in either the system or its surroundings. So this is basically, imagine that if you're watching a movie of some process and you run the movie backwards, you can't tell whether you've switched the movie around or not. So you can't tell whether the film looks exactly the same running forward and running backwards. A reversible process is an ideal process. Again, it's not something that happens in the real world. But when you take all the pieces in your system, when you include them all, the total entropy cannot decrease. That's what the second law of thermodynamics says. So let's think about a specific example here. So let's say I start with two containers. They each hold a kilogram of water. My container over here has a kilogram of water at 40 degrees Celsius. My container over here has a kilogram of water at 60 degrees Celsius. So basically this is, I've got hot water, I've got cold water. It's the same amount of water. I know if I mix these things together and put them into an isolated container, so again, if I work this as a calorimetry problem, at the end I would end up with 2 kilograms of water at 50 degrees Celsius. So the fact that I've got the same amount of water means that they're going to come to the average temperature of what they started with. In this case, it happens to be 50 degrees Celsius. So the energy has been rearranged, right? There was more energy with the 60 degrees Celsius water. There was less energy with the 40 degrees Celsius water. They exchanged energy, but the total energy of my system hasn't changed. I still have the same amount of energy that I did when I started. It's just that the hot water has given up some of its energy to the cold water. So I know that the energy hasn't changed. Delta E equals 0. But the entropy has increased. Again, this isn't a reversible process. You never put 2 kilograms of water at 50 degrees Celsius out, put that into a calorimeter and come back later and there's 1 kilogram of water at 40 degrees Celsius and another kilogram of water at 60 degrees Celsius, right? It never runs in that direction. We know that we're always going to end up with it running this way, never running backwards. So I know that this can't be a reversible process, and so the entropy here has to have increased. What that means is that basically we've lost the opportunity to convert some of this energy into work. So part of why we end up caring about entropy is that entropy is giving you some indication about the potential to use that energy in a productive way. So the way we use energy productively is to convert it into work, but when the entropy increases, I lose some of that ability to get that energy back as work. So this is why we care about entropy, because we'd like to keep as much energy as we can that has the ability to be converted into work. All right, so for a reversible process, we can, as I go from some state 1 to state 2, so if this is isothermal, I can define the change in entropy as simply the energy transferred into or out of my system as heat divided by the temperature. And the important thing about the temperature here is that this temperature is an absolute temperature. So that means it needs to be in Kelvin. So I cannot use Celsius for this calculation. I have to use Kelvin. The units of this, well, energy has units of joules, and our temperature has to have units of Kelvin. So the units of entropy have got to be joules per Kelvin. Notice, if I take in energy as heat, then Q will be positive, which means that delta S will be positive because my absolute temperature is always positive. Again, this is the beauty of using the Kelvin scale rather than any other, is there are no negative temperatures in the Kelvin scale. However, when my system loses energy as heat, then Q would be negative, which means that I would decrease the entropy. So thinking about whether my system is taking in or losing energy as heat will tell me the sign of what's going on with the entropy. So it is possible to have the entropy increase. It is possible to have the entropy decrease. But we'll come back and talk about why this can't be all that's going on in my system. So for us, we're going to deal with two particular ways in which where we can calculate the entropy. The first one will be an isothermal process. That's our latent heat process. It happens at a certain temperature. And so we calculate the energy transferred into or out as heat in a latent heat process by plus or minus the mass of your substance times whichever latent heat value you need. And so just plugging that in for Q tells me that I can calculate the change in entropy for a latent heat process as simply plus or minus mass times the latent heat value divided by the absolute temperature in Kelvin. The other process that we're going to care about is the specific heat process. Now, a specific heat process isn't isothermal, right? The temperature is clearly changing. I have a change in temperature. But you can go through and derive the expression for the change in entropy, and notice it's not as simple as simply Q over T. But here's the expression that we can use if we have a specific heat process. So mass times the specific heat times the natural log of final temperature over initial temperature. So these are going to be the two ways that we'll calculate the change in entropy for the two processes that we're going to be dealing with in our calorimetry problems. So let's come back to our example. So here's our 1 kilogram of cold water, 1 kilogram of hot water. We're going to combine them. We're going to end up with 2 kilograms of water at 50 degrees Celsius. And so the question becomes, since I know that my cold water is taking in energy as heat, so its entropy change has to be positive, and my hot water is giving up energy as heat, so its entropy change has to be negative. That begs the question is, am I violating the second law here? So I know that the second law says that for a closed system, which is what happens when I put all this stuff into a calorimeter, that's a closed system, it's isolated, that the entropy change for this process, because it's a reversible process, has to be greater than 0. But I know that one part, it's clearly negative. So for the hot water, the change in entropy is clearly negative. So why do I know that this isn't violating the second law? And so basically, what the second law tells us is that I need to include all the pieces taking part in my process if I want to think about whether or not I'm violating the second law that says the total change in entropy has to increase. And so for my system here, well, my system has two pieces. It has the cold water and the hot water that I started out with. So I need to think about doing two calculations, one for the change in entropy of the cold water, one for the change in entropy of the hot water. Since these are both, I know these are both specific heat processes, right? It's the same stuff, same phase, it's water in both cases. They're both changing temperature. So I can calculate the change in entropy of the cold water as mass of the cold water times the specific heat of water times the natural log of the final temperature they end up at over the initial temperature that the cold water started at. And again, I just need to make sure that both of these temperatures are in Kelvin. Same thing over here. I have a specific heat process that the hot water undergoes, so I can use mass of the hot water times the specific heat of water times the natural log of, again, the final temperature in Kelvin divided by the initial temperature of the hot water in Kelvin. I know that, again, Q was positive for the cold water, it was negative for the hot water. So I know that the entropy change has got to be positive for the cold water, the entropy change has got to be negative for the hot water. And so really whether or not I'm violating the second law of thermodynamics comes down to which one of these values is larger. And so the easiest way to do that is just to go ahead and do the calculations. And so when I calculate the change in entropy of the cold water, again, I know it has to be a positive value. It ends up being a positive value. I know it has to have units of joules per Kelvin. It does have units of joules per Kelvin. And so I plug in 1 kilogram times 4186 joules per Kelvin times the natural log, and again I have to put my 50 degrees Celsius and 40 degrees Celsius into Kelvin in order to plug them into this natural log function. When I take care of that, do it all correctly, I end up with the change in the entropy of the cold water is 132 joules per Kelvin. I can do the same calculation for the hot water. Again, I started with 1 kilogram of hot water. It's still water, so I want the same specific heat value of 4186 joules per kilogram. And again, I need to put the initial and final temperatures of the hot water into Kelvin, final divided by initial. And in this case, what I notice is this is a slightly less than 1 value. So when I calculate this fraction, it's slightly less than 1. The natural log of a number between 1 and 0 is a negative number. So the natural log ends up taking care of the fact that I know that the entropy change for my hot water is negative. But the important thing is this negative value of negative 128 joules per Kelvin is smaller than what it was for the cold water, the entropy increase of the cold water. So because the entropy increase of the cold water was larger than the entropy decrease of the hot water, then when I calculate the total change in entropy for my system, sure enough, I end up with something that is positive, which makes sense because I have a irreversible process that's isolated, so I expect the second law to hold. And sure enough, this tells me that the second law is inviolate. So what we're going to do in class tomorrow is basically deal with building on our calorimetry problems. We've really been doing sort of the first law of thermodynamics in the calorimetry problem. And now we're going to come back and add the second law of thermodynamics and talk a little bit more about what the second law